Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to sensors and transducers, and we'll extend our discussion on liquid level measurement in a container using mechanical transducers. We have covered bellows, we have covered Bourdon tube. In this video we are going to discuss liquid level measurement using thin plate diaphragms. So thin plate diaphragms we have covered. So a quick recap. So thin plate diaphragms, again, like bellows, like Bourdon tube, they are primary mechanical transducers. So what does that mean? Primary transducers means which gives non-electrical output. So basically it is physical movement, displacement, angular, linear, like that, rotation or linear displacement. So it responds to the changing parameter with respect to movement, to and fro movement, linear movement, angular movement, like that. So we have to use another transducer which is called as a secondary transducer, which converts that mechanical movement into electrical output, voltage or current. Now commonly used secondary transducers are LVDT, capacitive transducers, potentiometer, magnetostrictive transducers, or inductive transducers, like that, so that we get a proper voltage or current signal. Again, there has to be a proper calibration between the secondary transducer output and the primary transducer output. Okay, so that is the basic principle. So again, coming back to thin plate diaphragms, so it is a primary mechanical transducer. It is basically a circular plate, thin plate. It is, as the name suggests, it's a thin circular plate which is made of special metallic alloys. Okay, and the commonly used metallic alloys, they are bronze, phosphor bronze, beryllium copper, stainless steel, like that. So as I said, the thin plate diaphragms, they are made of special metallic alloys, which is bronze, phosphor bronze, beryllium copper and stainless steel. And the choice of the material, its shape, its size, the dimensions, they particularly depend on the magnitude or the how much more pressure or how much less pressure, the range of pressure which is to be measured. Okay, that determines the choice of material, the size of the material, the shape. It is circular, but the radius and all that depends on this. So this is the general structure of a thin plate diaphragm. It's a circular shaped with a certain thickness T and the radius R. Material selection, radius, all that depends, thickness, it depends on the range of pressure that has to be measured. So here certain things have to be taken care of while designing the thin plate diaphragms, which is the ratio of the diameter to thickness. It may vary from 25 to 100, with thickness ranging from 0.1 millimeter to 5 millimeter. And generally this plate is kept clamped between the two flanges, two fixed points. Okay, and also in certain cases it is welded around the circumference, and then it is subjected first, when in the design phase, it is subjected to test whether it is capable of handling the pressure, the force, and then after that it is put to actual use. So here the thing is, when the diaphragm is subjected to force or pressure, okay, it is subjected to the force or pressure here. So here, when it is subjected to external pressure, in that case the diaphragm, it undergoes, as it is flexible, it tries to kind of expand in the other direction, which leads to linear displacement of this tip position, this position here. This is the initial position, then this is the final position. So this linear displacement and the applied pressure, this forms the input and output relationship. The input is the pressure, the output of this first stage primary mechanical transducer, that is linear displacement. Pressure and linear displacement. Okay, this. So there is a relationship between this two. So the pressure difference, that is the external and internal pressure, okay, on one side, both the sides, okay, that is not external, internal. This side pressure on, let's say this is side 1 which has pressure P1, and this is the other side 2, area 2, where the pressure is P2. So if P1 is greater than P2, the pressure difference is always P1 minus P2. If P2 is greater than P1, that is P2 minus P1. Okay, that is the pressure difference. Higher minus lower. So that pressure difference is equal to 16 E T to the power 4. E is Young's modulus of elasticity. T is the thickness of the thin plate diaphragm material. Then by 3 R to the power 4, R is the radius of the thin plate diaphragm, 1 minus mu square, mu is the Poisson's ratio, into Ym, which is the maximum linear displacement. Okay, this is the maximum linear displacement, or the linear displacement in that case divided by the thickness, plus 0.488, again maximum linear displacement by T to the power 3. Okay. This is for the maximum condition. Again, for that particular instantaneous displacement, we can simply put Y, that particular displacement. Okay. So this is the relationship. Now we have to use it for measurement of the level of a liquid column. So like bellows, like Bourdon tube, principle is same. When we have a certain liquid in a container, in a tube or whatever, because of its height above the reference of the datum position, it will exert some pressure. That pressure is equal to this. PL is equal to rho GH. Rho is the density of the liquid, G is acceleration due to gravity, and H is the height of the liquid from the reference position. This is the reference level horizontal position from that edge. Again, there are two conditions here. If the lid is closed, only liquid level pressure will be measured by the sensor. If it is exposed to the atmospheric pressure will come into play, and the total pressure, okay, the total pressure P atmosphere plus the liquid level, that is measured by the sensing element. So here the sensor, which is this diaphragm, which is actually in this kind of a arrangement, is present, where we have an encapsulation chamber, then we have this diaphragm, thin plate diaphragm, connected to the two flanges, two fixed points, the supports, and then we have a tubular kind of arrangement which is connected to the source of pressure, the connecting tube. Okay, so when it is connected to the liquid column, because of the level of the liquid column, the height of the liquid column, it will exert some pressure combined with the atmospheric pressure, as a result of which, depending upon the the pressure on both sides, the diaphragm will either expand or get compressed, okay, like that. So that will cause a linear displacement, okay, this, and using this relationship we can determine the differential pressure. When one side pressure is known, the other side pressure can be calculated. Okay, so here when the pressure is known, the total pressure which is measured, okay, the total pressure which is measured by the sensor, that is the liquid column pressure and the atmospheric pressure. The atmospheric pressure is constant, so we will subtract it from the sensor reading, and that will give us the liquid column pressure. So here there is one important condition, which is the density of the liquid that should be known. Okay, that should be known. So when we get the liquid column pressure, we will get the height of the liquid using this relationship, because we get this from the sensor, the liquid column pressure, by subtracting the atmospheric pressure from the sensor reading, and the density is known, acceleration due to gravity is known, so we get H is equal to P L by rho g. Okay, this is when the lid is open. When the lid is closed, the sensor reading directly gives us the liquid column pressure, because atmospheric pressure in that case is 0, because the lid is closed. So the sensor reading directly gives us the liquid column pressure. So the other case, we have to subtract the atmospheric pressure from the sensor reading. So from this we get the height or the level of the liquid in the container or the tube. Okay, so this is the basic relationship. Okay. So here let us try to understand this whole thing from a three-dimensional perspective. So here we have a liquid column, a liquid in a container, which is at a certain height h above the reference. The diaphragm is connected to the liquid column through the connecting point, and it measures both the liquid column pressure and the atmospheric pressure. The liquid column pressure because of the changing level or height of the liquid. So this is the connecting point. So this whole thing, it comes in the form of a encapsulated chamber container. So when it is subjected to the pressure, the diaphragm, it either expands or compresses. So this is the maximum point where the tip of the diaphragm, it touches the container. Okay, so because of the liquid column pressure combined with the constant atmospheric pressure, the thin plate diaphragm, it undergoes expansion and compression. Expansion, the maximum point; compression, which is the minimum point at the bottom. So here, through the formula which we established, the displacement, the axial displacement, here it is happening along the y-axis, from the tip of the diaphragm to the reference position, we establish a relationship between the axial displacement from the bottom tip to the top tip of the diaphragm and the differential pressure, that is the internal and external pressure, the pressure inside the diaphragm and the pressure outside the diaphragm, which is connected to the liquid column and the atmospheric pressure combined. So this is, we measure the axial displacement from the tip of the diaphragm to the original reference position, the axial displacement happening along the y-axis. Okay, so this is the basic principle of liquid level measurement using thin plate diaphragms. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you very much.